All right, we're in the end game at this point, as I mentioned in the last video. What we're shooting for here is essentially everything from section 1.2 through 1.4 was really for this. So we want to come back and take a look at argument analysis instead of having to rely on Venn diagrams and figuring out how to interpret sentences into set relationships. We're going to use the format of truth tables and symbolic logic to analyze whether or not an argument holds up. So hopefully it stands to reason the first thing we're going to need to do is take a verbal argument and turn it into symbolic form if we want to do all this truth table stuff on it. I mean, I can't fit many sentences on the board, right? So I think it's often best to take a look at this in the context of an example to which we already know the answer. So what we're going to do is revisit that very first example from section 1.1 when we did argument analysis about Sir Isaac Newton, and see how this truth table, symbolic logic structure holds up for that particular argument, because we already saw through Venn diagrams that it's valid. Okay, so we've got to figure out how to turn that argument into symbolic form. So, quick reminder, PowerPoint slides on Moodle. I don't have room for all the words, so keep them handy. All right, so the first hypothesis in that argument, we called them premises then. The book refers to them as hypotheses now. I apologize. They shift gears. I wish they hadn't. So just roll with it because it makes the lettering a little easier to follow. All right. So the first hypothesis of the argument said that all mathematicians are logical. Then we have Sir Isaac Newton, a specific person, was a mathematician. The conclusion says, therefore, he was logical. All right. So we need to identify some simple statements, and then we're going to need to translate the sentences in our argument into a symbolic format. Okay, so the first thing that jumps out at me is we're told somebody is a mathematician. So I'm going to call statement P, a person is a mathematician. Technically, somebody's name comes up in here, but the structure holds up regardless of who the person is. I need one more simple statement because we have a person is logical showing up in there. So, and that's really all we need here. Like I said, technically Sir Isaac Newton's name shows up, but it's kind of there for decoration. You could change out anybody's name if you wanted to go dig up famous mathematicians, and same structure holds up. Okay, so we've got someone's a mathematician, someone's logical. All right. So now we need to take those sentences in our argument and represent them symbolically. All right. So the first hypothesis, I'm going to label it H1. Here's where the labeling comes in handy. So that first hypothesis says all mathematicians are logical. Hopefully you'll recall from section 1.2, we said we can translate that as the conditional, if someone is a mathematician, then they are logical. So that's a conditional. And it uses P first. P is with the if they're a mathematician, then they're logical. So we have P implies Q. That's the first hypothesis in our argument. Secondly, it says someone is a mathematician, or was. I tend to play fast and loose with verb tense, so you get the idea at this stage. So our second hypothesis is someone is a mathematician. Again, I guess if you really wanted to, you could clutter this up with extra statements, but it doesn't really impact the structure. It's just adding complexity to be complex. So hypothesis 2 is simply the statement P. And then the conclusion, the therefore, we represent generally with the letter C. So we have hypothesis 1, hypothesis 2, and conclusion. If you want the therefore, you can do the diamond from the PowerPoint slides. The textbook uses that triangle of dots that I couldn't figure out how to make in PowerPoint. But the conclusion says Sir Isaac Newton was logical. Again, taking Newton's name in there as kind of fluff. That's how the argument breaks down structurally. If a person's a mathematician, then they're logical. We have a mathematician, therefore that mathematician is logical. That's our symbolic structure. Okay. Now we got to dig in and figure out exactly how we're gonna analyze this beast. That can get a little bit tricky. So you'll notice on the slides, I've got sort of a compound statement that ends up giving us a way to confirm whether or not an argument holds up. So if we have a pair of hypotheses, H1 and H2, like them, and a conclusion, like this, the argument structure we've got here is valid in precisely one situation. You see that if and only if thing that shows up in the slide. So what we need to take a look at is this thing. So it's a big conditional, and there's some pieces that go into it. Bear with me, like I said, we'll walk through this. But the idea is this thing needs to be true no matter what's happening for the individual, simple statement truth values that go into it. Regardless of true-false combinations, we should get all true results at the end of our truth table. So sort of our punchline here if this is true, no matter what's happening for the simple statements that go into it, that's what logic experts call a tautology. So if that happens, then the argument's valid. If there is any possible permutation of true and false values for the component statements that makes the argument false, or that makes that, this compound statement here false rather, then the argument is invalid. It doesn't hold up. Okay, so now we've got to investigate this thing, and here's where we need to kind of break stuff into chunks, and I have to do another one of those jump cut things. Sorry. And voila, we have the start of the truth table sitting here. So we have the true and false permutations for our two simple statements P and Q, and now what we need to do is walk our way through the structure to get us to that kind of punchline guy, the H1 and H2 implies C. So first off, our first hypothesis is our standard conditional, P implies Q. By now, hopefully, this format holds up. Conditional is only false when we have true implying false. Other combinations, all considered to be true. We've got hypothesis 1. Hypothesis 2, in this instance, it's really just the statement P. So I can kind of copy and paste, right? I just need to take this. I don't need to do anything fancy with it. I just take it and lift it. If we're doing this in Microsoft Excel, I just highlight the cells, Control C, Control V. So okay. So now we've got H1 and H2. I've already let the cat out of the bag on what we're going to do next. Let's go ahead and do that conjunction, because in our big endgame statement, that was in parentheses. I don't know. I've done really well so far. I'm bad about doing that. I've done real well with not writing an A when I try to do that little caret thing. All right. So H1 and H2. Again, this is a conjunction. It's only true when both statements that go into it are true. That happens right here, not right there, or neither of those places. So we have a true, and then a bunch of false results. Okay, we got that. Now we need our conclusion statement, C. That was just Q. So person is logical. I just copy and paste this into that particular spot in a truth table. I've got that. So I have H1 and H2. I have C. Now for the end game. I really need to stop saying that. I haven't even seen that movie. Weird, huh? So, all right. So H1 and H2 implies C. So now these guys are set up so they're right next to each other in the diagram. That's super duper handy because I don't need to worry about labeling L or R or anything like that, and they're already in the right order. So we have true statement implies true statement. That's true. False statement implies false statement. As we said before, that one works out to be true. False implies true is true. False implies false, also true. Okay, so we're done. We've got the column that represents our big statement that kind of condenses the entire argument together. And as you can see, I have nothing but true values floating through here. So let me erase these extra lines I drew at the bottom. Based on that, our argument is valid, which is reassuring because, we figured out he was valid last week. So All right, so that's basically got our structure laid out. You'll notice I've got this boiled down into a 5-point process in the PowerPoint slides. So if you want to keep that handy, it does break this down. Represent arguments symbolically, work out truth values for hypotheses, put them together with a conjunction, truth values for conclusion, put it all together with this guy at the end. So I find step-by-step processes often help students follow what's going on. So we've seen that this works for one example. I obviously plan to take a look at some others, so stick around.